All right, tonight what we're going to be talking about is percent yield. And what percent yield is it's very important to scientists and chemists and industry. And what it does is it tells you how much do you get out of how much you should have gotten. And the higher the percent yield, obviously the better for industry. Now, during some chemical reactions, a great yield might be 99.99%, whereas during other chemical reactions, it might be good to even get 0.1% of product off of what you really want. But what it is it's basically the mass of the actual yield, so what you got in lab, divided by the theoretical yield times 100. And theoretical is an ideal, so best case scenario, how much could you have gotten? So there's two formats that you could use, and both of them are the exact same way, just rearranged. Here's one formula where it solves literally for percent yield, and you take actual over theoretical times 100. And the other way that I found successful with students is once again using proportions. So you take actual over theoretical equals your percent yield over 100. All right, so what is the actual yield? Once again, it's the mass that actually forms during a lab. So it's what you got in a lab. Not what you should have gotten, but what you actually got. It's very similar to tests. It's what you actually got in tests versus theoretically what should you have gotten. If I got a 20 out of 30, I actually got a 20. I theoretically should have gotten a 30. So theoretical is the maximum amount, typically in mass, of product that you can expect to form in a chemical reaction. So how much should you have gotten if everything was rainbows and sunshine? All right, to solve percent yield problems, what you need to do is set up a BCA chart. And the question will be provided a mass or an amount of some sort. And so when you try to use a BCA chart, you're going to need to make sure that you go only put moles in that table. So the first example that we're going to do is actually without a BCA chart, and what we're going to do is we're just going to think about it. So in a lab, you recover 20 grams of product, but we're expected to get 25. So the 20 grams would be your actual. Your theoretical would be 25, what you should have gotten. What is your percent yield? So we're not even going to really do this quite yet. But what the question is which will always be less, actual or theoretical? And the reason is the actual, and the theoretical is just an ideal. It's not really a reality most of the time. And why do you not always get 100%? Well, because people are making these solutions, so therefore you can drop some of the sample, knock over a beaker. These are like lab errors. Ones that typically happen is that you'll leave some of the sample behind when transferring containers. So think about when you are like making cookie dough. It's how well did you scrape off that cookie dough from the sides in order to make your cookies. If you're like me, sometimes I leave it purposely still in the pans or in the bowl so that I can actually lick it later or eat it later and not cook my cookies. But typically it's basically how well did you scrape everything off of one container to transfer it to another container. Sometimes you'll have reactants that actually have contaminants in it and therefore they're not pure, so therefore the reaction doesn't work as well as it should. And then a lot of times you'll also have side products made where you make a substance that isn't actually talked about in a chemical equation, just because that's how some chemical reactions occur, depending on the conditions that they're made under. So we're going to do a straight out problem in a reaction between 15 grams of beryllium, so I'm going to put a 15 grams of beryllium up here, and an excess of hydrochloric acid, so I know I can immediately fill in excess and excess. Beryllium chloride and hydrogen gas are formed. Now right now this looks just like a straight out sentence, but if you read on further it says what is the theoretical yield of beryllium chloride. So this is the one that I'm trying to find out. So in order to use this BCA chart, what I'm going to need to do is I'm going to need to convert the 15 grams of beryllium into moles. So it's going to be 15 grams of beryllium over X moles of beryllium, and that is going to equal its molar mass, which if you look at the periodic table is 9.0 grams of beryllium for every 1 mole of beryllium. When you cross multiply, you get X equals 1.6 moles of beryllium. Now, whenever you are filling in this BCA chart, these are always your theoretical. So in an ideal world, if I put in 15 grams, how much beryllium chloride could I produce? Well, I know that I produced I started with 1.67 moles. I'm going to assume that it goes to completion, which means that it would lose absolutely everything. So I would end up with 0 moles of beryllium. Now, if I look at my coefficients, I've got 1 and 1, so this is a really nice problem. So I started with 0 moles of beryllium chloride, because I always start with 0 of my product, and then I'm going to add 1.67 moles. The reason, once again, why you don't need to do any math is because they have the same coefficient, so whatever I lose of beryllium, I'm going to make in beryllium chloride. It's a 1-to-1 ratio, so that means I am going to produce, theoretically, 1.67 moles. Once again, anytime you fill in the BCA chart, you are dealing with your theoretical. So now I'm going to continue and change my 1.6 moles of beryllium chloride into grams to figure out my theoretical yield in grams. So I'm going to set up a proportion of 1.67 moles of beryllium chloride, and that is how many grams of beryllium chloride. So I'm going to set that equal to the 1 mole of beryllium chloride, which has that should be a Cl2, sorry I ran out of room, over 80 grams, which is the molar mass of beryllium chloride. Once you cross multiply, you end up getting 133.3 grams, which rounded to sig figs would be 130 grams. So theoretically, in an ideal world, I would produce 130 grams of beryllium chloride. Alright, so what is the theoretical yield? That would be the 130 grams. Now, if only 0.4 grams of beryllium chloride were produced, what's my percent yield? So I'm going to fill in my formula of percent over 100 equals actual, which I'm going to abbreviate as A, over theoretical. So I am asked about the percent yield, so I am asking you to solve for percent. So I'm going to do percent, which is kind of my x, divided by 100, equals my actual, which it says I got of 0.4 grams of beryllium chloride. Now if I multiply or I divide it by my theoretical, theoretically I should have gotten 130 grams of beryllium chloride. So that doesn't look like a very good percentage. So when we cross multiply and multiply by 100, we actually get my percent yield is 0.31%, which rounded to the 1 sig fig would be 0.3% yield. All right, let's try the next one, which is a reaction of 73 grams of aluminum. I'm going to put 73 grams above and an excess amount of oxygen. So I know that I can fill in my excess here and my excess here for my oxygen. And then I am going to once again look ahead, and the question asks what's the theoretical yield of aluminum oxide. So I'm going to need to figure out this guy right here. So in order to use my BCA chart though, I need to be in grams, so I'm going to convert my 73 grams of aluminum into moles, which means I need over moles, x moles of aluminum. So that is equal to 27 grams of aluminum over 1 mole of aluminum. Cross multiply and you get 2.7 moles of aluminum. So I know that I started with 2.7 moles of aluminum. I am going to assume that it goes to completion, so I'm going to lose 2.7 moles, which means I'm going to end up with 0 moles of aluminum. Now, because I'm only caring about this, I don't need to worry about my oxygen. If I look at my coefficients, I have a coefficient of a 4 and a 2, so I am going to need to do my molar ratio. So I'm going to convert 2.7 moles of aluminum, and I need to figure out how many moles of aluminum oxide that is. So that is equal to 4 moles of aluminum over 2 moles of aluminum oxide. So when you cross multiply this, you get a total of 1.35 moles of aluminum oxide. So as with everything, I always start with 0 moles of my product started. So I'm going to add or be able to produce 1.35 moles of aluminum oxide. And so therefore my total I'm going to have as a product ideally would be 1.35 moles. So when it says what is the theoretical yield, I'm going to convert into grams. And so I'm going to do 1.35 moles of aluminum oxide over X moles, or I'm sorry, X grams of aluminum oxide. And that is proportionally equal to its molar mass, so it's 1 mole of aluminum oxide over 102 grams of aluminum oxide. So when we cross multiply this, we get, ideally, because I use my BCA chart to solve this, I should produce 138 grams. Okay, rounded to the right number of sig figs, you should get 140 grams. But I only recovered 71.6, so once again, I'm going to need to fill in my percent to solve for my percent yield. I'm going to do percent over 100 equals actual over theoretical. My actual was what I got in the lab, so that would be 71.6. My theoretical is what I got using my BCA chart, so that is over 140. And that equals my percent over 100. So when I cross multiply that, I get 52%, which is a much better yield than my original one from example number 1. All right, hopefully you have a basic understanding of percent yield, and see you tomorrow.